Hey geometry students, welcome to our notes on trapezoids. So on Tuesday, you and your group in breakout rooms explored a new shape called a kite, which was another quadrilateral or four-sided figure. This is our final quadrilateral that we're going to be looking at together. And next week we're going to be moving on to a new unit. So this is going to close out our unit. And what I'd like you to do is to pause the video and write out these questions in your notebook or wherever you're taking notes. And you're going to try and draw a picture of a quadrilateral marking these two restrictions. Unpause when you're ready to discuss. So for the first one, for number 1, we needed a four-sided figure or a quadrilateral with only one pair of parallel lines. Now notice on the side I've drawn examples that we've seen where we have two sets of parallel lines, rectangles, squares, rhombuses, and then remember a parallelogram, this one I'm circling here. The parallelogram was the overarching category, and remember all of these rectangles, squares, and rhombuses are special parallelograms where we either have all sides being equal like the rhombus, or we have all angles being equal like the rectangle. And then remember the square was the really special parallelogram where all sides and angles were equal, so it had all the qualities of a rectangle and a rhombus, was getting us a square. So that was what we've seen before. We also saw kites, right? Kites don't necessarily have to have parallel lines, but sometimes they can, right? Kites, all we know is that all we have to have be true are that the sides next to each other are congruent, but remember some of you guys saw in explorations that sometimes they could have parallel sides, just not always. Here are some examples of shapes that have one set of parallel lines. Right, notice the angles are kind of varying. I tried to give at least a couple of different ways that you might have sketched it. And now for number 2, you're going to try and do one where the non-parallel sides, right, in this case, like these are the non-parallel sides, right, the ones that are not highlighted yellow to show that they're parallel. Remember the marking diagram symbol for being parallel are these kind of arrows. It's almost like it's along the line, so it looks like an arrow. But that's just how we indicate to our readers that they're parallel. We're going to try and make, in number 2, the non-parallel sides congruent. So this is probably the most common visual for number 2 that most students will draw. Notice I've shown that the non-parallel sides have tick marks to indicate that they're equal. Okay. And then if we go to the next page, here's our notes. The shapes that you just created in the warm-up were blank and blank. I'm going to kind of label it over here. So number 1, you guys were drawing trapezoids. And then number 2, this is a special type of trapezoid called an isosceles trapezoid. And an isosceles trapezoid is really similar to an isosceles triangle. So as we talk about them, right, this is the trapezoid and the isosceles trapezoid. It might be good to kind of think about them within like the family tree of quadrilaterals. So I'm going to kind of take what I drew here, right? I'm going to kind of take this stuff, I'm going to move it over here and kind of discuss over here. So we have the shapes with 2 sets of parallel lines, right? This one is no parallel. That's for our kite. Remember you saw in the exploration that occasionally kites can have parallel lines, right? Because the only thing that has to be true is sides next to each other have to be equal. So remember, a square was a really special type of a kite where all sides were equal, right? Notice sides next to each other are equal, not just across. So occasionally they can have parallel lines, but they don't have to. And then we're seeing the one parallel set, right? We've got our trapezoid, and I'm just going to kind of do that, do one like this, right? Do this one that you guys saw, and I'm going to use my parallel labels. And so we have the regular trapezoid, we have the isosceles trapezoid, and then this one over here, if I make it a right angle, kind of intuitively, we would call that a right trapezoid. Just like if you have a right triangle. So isosceles trapezoids are actually really similar to isosceles triangle. Think about an isosceles triangle, right? We've got those base angles are equal. So in this case, the base angles are also equal to each other. And then one thing that's interesting, if you were to explore this, I can find a GeoGebra one for us if people are interested. The upper angles are also equal. It's kind of a nice feature. And that's coming from the fact that the lower angles are equal. That kind of dictates that just based on the lines being parallel and summing to 180, the smaller angle and the bigger angle. So we'll see what that looks like. And I've got a couple of little examples with some angles. So just to kind of practice, right? The question is, why do those angles, like in the example number 1, why do angles C and D technically have to add to 180? The reason why comes back to what we learned about with just parallel lines previously. If I extend my parallel lines, if I extend this line, notice this looks like a pair of parallel lines cut by what we called a transversal. You don't really have to remember that term. You just might recognize it. Remember, we did see that these angles were equal, right? And these angles were equal. And remember, the two angles next to each other added to 180. So that means that the pink angle and the purple angle, right, any pairing of those would add to 180. So that is why we're allowed to assume that 8x plus 34, 7x minus 4 equals 180. That's saying that angle, the two angles add to be 180. And that's just coming from our parallel line properties. I'm going to combine my like terms. 15x's and 30 equals 180. I'm going to subtract 30 on both sides. And 15x is equal to 150. Notice that the numbers there work out really nicely. Divide by 15, and we'll get that x is 10. Now they specifically asked us to find the measure of angle C. What they're asking for, if I erase this stuff, they're asking just for this angle here, right? We had it kind of labeled pink. So that would be 8 times 10 plus 34 for our amount of degrees. 80 and 34. I know 80 and 20 would make 100, right? So I'm going to take 20 away from 34. That would leave 14 left. So it's looking like 114 degrees. Okay, so that's one important thing, that in the trapezoid, if those are parallel, we would be able to assume that those two angles would add to 180. So keep in mind some of those parallel line ideas are going to keep coming up in this topic. For the next one, we've got an isosceles trapezoid. Notice those markings. So if you remember what we were looking at here, right, base angles are equal for isosceles trapezoids and triangles. We can then assume that this bottom angle E is also 49 degrees. But now they want us to find F. We're going to use the same idea as before, right, that angle F plus angle E adds to 180. Same thing if you did angle G and H. So 180 minus 49. Would be 131 degrees for angle F. Okay. So those two are kind of getting us used to some of the angle properties of trapezoids. There's also some other properties to explore here. Remember, as always, do pause the video as you need to be able to write out the problems. Some of you may have printed. If you prefer printing, that's always good too. So number 3 gives us that J to N is 10.6 long and N to L is 14.8 long. And they ask us to find how long KM is. Now, most of you guys are going to kind of guess correctly, which is that for an isosceles trapezoid, right, if I have isosceles trapezoid, these two diagonals are going to be congruent or equal. So diagonals are equal in length or congruent. So that's kind of like the intuitive thing. I normally will give students this question and they'll kind of make the leap themselves that, oh, they seem like they should be equal just based on everything else that's already equal in this problem, and you would be correct. Okay, so 10.6 and 14.8, right? That combines to be 25.4 units. We don't really know what the units are, so you could put units or just leave it as it is. The perimeter of the isosceles triangle below is 164. We're going to look for x and y. Notice we've got some angles given. They did say it's isosceles trapezoid, so I'm going to mark that those sides are equal, and I'm also going to mark that these angles are equal here. That means that this is 81 degrees. If I wanted to figure out what 7x is equal to, I could subtract 81 from 180. It's going to be, well, I guess they don't have letters. I was going to put the angle of whatever letter that was, but we do not have letters for our points. Okay, so it's going to be, it looks like 99 degrees. So that means 7x is equal to 99. Okay, if I divide by 7, that would tell me what x is equal to. And according to my calculator, it's not super clean, so I'm going to put approximately instead of equal to. That's just if you are rounding, that we generally use the curving lines rather than the straight equals. About 14 point, I'm going to round it 2 decimal points. It's 142, but since 2 is smaller than 5, I'm going to round down to the 4. So that's approximately what my x is equal to. And then to find my y, I know that the two sides are equal, right? Because of isosceles, it's kind of like an isosceles triangle, like on its side, right? It almost looks like something like this, but with a trapezoid shape. So if I know the perimeter is 164, that means all of the sides, right, added together would equal that. So I'm just going to sum them all up. Y plus 12, another y plus 12, right, because they're the same. The one base is a y and the other base is a y minus 12. That all combines to be 164. I'm going to put all my like terms together, my y's and my 12's. Looks like I've got 4 y's. These 12's are going to make a 0, so I'm just going to make it 4y plus 12 is equal to 164. Subtract 12 on both sides, and you've got 4y is equal to, looks like 152. Divide by 4, and on my calculator I'm just double checking what that is. So 152 divided by 4, looks like it's going to be 38. Okay, so we've got our x and our y. We've got one more problem just to explore trapezoids in different spaces. So we've mainly been focusing on sides and angles of trapezoids. We're now going to be looking at a trapezoid on the coordinate grid. Okay, so I've plotted the 3 points and color coded, and you can kind of start seeing like the general shape of what our trapezoid will look like. Notice it is an isosceles trapezoid, which means that we're going to have those sides be equal. Now, in order to figure out the different answers, right, part A asks us for the equation of the line that the longer base is on. So here's my longer base. They'll call that the longer base and the other one the shorter base. So they'll refer to these as bases, just so you guys know. That would be a good thing to put at the top of your page with your picture, right? So feel free to go back and maybe in our family tree space right over here, maybe label that this is a base, right, as is this, the sides that are parallel. So we know that those lines are parallel, so the first thing I would want to do to kind of figure out what the bottom base is like, because I don't know where that 4th point is, I want to figure out what the slope of my little base is. So I'm going to find my slope. Okay, my slope work is in red. It looks like it simplifies to -1/2. So I'm going to take that slope and I'm going to extend. So from my blue point down 1 over 2. And I'm going to keep doing that. And I'm just going to continuously plot those points. Okay, writing my equation of my line following mx plus b, or slope-intercept form, is kind of color-coded there. The last question is, where is my 4th point? Take a look at the green triangles. You'll notice the 1 and 3 sides. That means the third side of the triangles also have to be the same. You can also double check the point you found by plugging in that x of 4 and finding the y of -3 in your